Alright, in this video we're going to be looking at mostly graphs of functions. So we're going to be looking at intervals of increasing, decreasing, and constant behavior. We'll also look at minimums and maximums. That's the same thing as extrema. If we let y equal f of x be defined on an interval I, f of x is said to be increasing on I if for each x1, x2, and then you see that funny looking e, that means element of or lives in. So for each x1 and x2 that are in the interval I, if x1 is less than x2, then f of x1 is less than f of x2. So we can draw a little picture to illustrate that. So there's your function f, and you notice that it is increasing from left to right. So if you wanted to draw like a little skater or something on there, they are going uphill as we read left to right, uphill as we read left to right. Here's our interval I, here's our x1, here's our f of x1, here's our x2, and here is our f of x2. Okay, so x1 is less than x2, and f of x1 is less than f of x2. So we are increasing. When we talk about increasing, decreasing, and constant, we'll always be referring to along the x-axis. So don't tell us ordered pairs, only the x-axis. Okay. All right. So if we're going to look at decreasing, let's speed it up a little bit. It's going to be very, very similar. So f of x is said to be decreasing on I, so that's an interval, if for each x1 and x2 in the interval I, if x1 is less than x2, then f of x1 is going to be greater than f of x2. Okay, so I had that backwards. All right, so there is our inequality. Okay. Alright, so this time if we draw our little person on their skateboard, they are now going downhill. Okay, so they're going downhill as we read left to right. Left to right, so we're always going to read left to right. So there's our function, here's our interval, and then here's x1, f of x1, here's x2, and f of x2. Okay, alright. Now you see that x2 is bigger than x1, but f of x1 is larger than f of x2. Okay. The last one we have here is constant. Constant means horizontal or flat. Okay. So pretty much the same thing as the other ones. If f of x is constant on I, interval I, if for each x1 and x2 in the interval I, we'll just go ahead and say one of them smaller than the other. This part doesn't really matter, but we'll just make the assumption that x1 is less than x2. Then f of x1 is equal to f of x2, so they're equal to each other. So we're going to be flat at that particular location, or that particular part of the graph on this interval I. So there's x1, f of x1, and x2 and f of x2. So here again you see x2 greater than x1, but f of x1 and f of x2 are actually at the same height. Alright, let's go ahead and do some examples. So here's the graph. This can be found something like this on Lumen homework. We'll have something like this. This is also the same graph in your notes. I've gone ahead and drawn in those red arrows there on the graph there. It's implied that it continues indefinitely in both directions. So we're going to go through a number of questions or things to find about this thing. So increasing we'll look at, decreasing, constant, domain, and range. So we're going to find all of those things. There's other things we can find on this graph, but we'll do those, and maybe I'll mention mins and maxes if I remember. All right. So first thing we're going to look at is where is it increasing? So where are we going uphill as we read left to right? Well, let's see, looks like it kind of starts at -10, but we're gonna keep going uphill from negative infinity all the way up, and we're gonna stop at -8. So you only do x-axis, don't do anything with the y-axis. Only the range we talk about the y-axis. Okay, so it's gonna be -infinity to -8, and then we're going to do minus 3, and so we got this steep slope here, minus 3 all the way up to minus 2. We are going uphill again. Okay. If you're wondering, I use commas for increasing. I'm not going to be picky about if you're using union. If you're looking at the formal definition that we had on the previous slide, using union technically doesn't work, but I'm just looking for where is it increasing. So if you tell me a union as opposed to a comma, that's okay. Anyways, let's go ahead and continue, and we'll find where we're decreasing. So where are we going downhill? Okay, so where is that decreasing? Looks like from minus 8 to minus 6. Yes, from minus 8 to minus 6. That is where we're decreasing. One other comment, some books might use, or some resources might use brackets as opposed to parentheses. I use parentheses. The homework we're going to do uses parentheses, so I would stick with parentheses. It depends on how increasing, decreasing is defined, but we're going to stick with parentheses. Okay, so we've got an increasing, we've got decreasing, and then the constant portions are where it's flat. So we are flat from minus 6 to minus 3, and we are also flat from negative 2, and then it's going to be flat indefinitely. It's flat the whole rest of the way. We'll go ahead and find the domain. That's the far left to the far right. So this function is going to extend indefinitely in both directions. So the domain is going to be negative infinity to infinity. It's going to be everything. And then the range, that arrow over here is going to go down forever, so it's going to go down to negative infinity. But you see it's capped off at 7. That's as high as it goes. And it actually achieves the value of 7, so that means we can include it. So including means bracket. So minus infinity all the way to 7. Now, the only one of these that actually we read off the y-axis, we took y values, that was the range. Increasing, decreasing, constant, and domain is always communicated with the x-axis. Since we're here, we can also talk about mins and maxes. So here would be a maximum. Well, I'm going to try to. I appear to have trouble drawing on this thing. Right there, that's maximum. That's king of a hill. This one's a little bit more complicated, but that's what a maximum looks like. This whole region here, that would be a minimum. It's the lowest point there. Now that's what we call local. Of course, over on the left here, it goes down indefinitely. So within a region locally that I'm circling here, that's the minimum. And then it's a little weird, but over here, this is the maximum. That's actually what we call a global maximum. Global is the tallest or highest point the function goes. It does not have a global minimum because it goes down indefinitely. Okay. All right, let's continue on, and we're going to look at another graph, and we're going to ask a million questions as we interpret what's on that graph. Okay, so here's the graph. Again, you'll have something pretty similar to that in the homework. Then you'll have this exact same one in the notes available on Blackboard. Okay, so I went ahead and drew that arrow in at the bottom there because where it's understood it's going to continue indefinitely. So the first thing we're going to look at is the domain. That is the far left to the far right. So it's got a dot at minus 4 on the x-axis, so the domain's going to start at negative 4, and then the arrow down here is going to go indefinitely, so it's going to go all the way off to infinity. For the range, the lowest this thing goes is, if we look at that right-hand branch there, that's going to go to negative infinity. That's the lowest it goes. The tallest it gets is 6, and it actually achieves the value of 6. Okay, so that's your range. Okay. Then we got a new thing we're going to look at. We're going to find the zeros, and we say the zeros of a function. That's where we either touch or cross the x-axis. So basically, where do you touch the x-axis? Okay. So zeros, that's going to be where the graph touches or crosses the x-axis. And so I say two places where that happens, negative 1 and also 12. If we want to talk about the x-intercept, that's going to be your zeros as an ordered pair. So the location is negative 1, 0, and 12, 0. Okay. I guess if we wanted to find the y-intercept, we didn't ask for the y-intercept, but here's the y-intercept. It wants to select instead of letting me draw on the graph here. But the y-intercept looks like to me to be about 0, and probably about a 1/2 is the location, in case they ask. I don't think they ask in this set of problems, but that's the y-intercept, 0 and 1/2. Okay. The next question they're going to ask is, okay, what is f of negative 3? And that question is, how we translate is, what is the y value when x is equal to negative 3? Okay, so when when x is negative 3, the height of the function at negative 3 is going to be 2. Okay, we'll ask another question, what is f of 7? So the height at 7, when x is 7, the y value is 5. So f of 7 is equal to 5. Okay. Is f of 5, is that positive, negative, or 0? So they're asking you, what's the y value when x is 5? Is it positive, negative, or 0? Well, f of 5 is 6, so that's positive. Okay, what's the number of times y equals f of x, or the graph, intersect y equals 2? And we'll talk about this a little bit more in a little bit here, but y equals 2, that's a horizontal line at height 2. So we're going to go ahead and draw a horizontal line at y equals 2. So 1, 2, and 3 places. So it intersects y equals 2 3 places. 3 times. Okay, we're going to move up to the upper left-hand corner, run out of real estate. For what values of x does f of x equal 6? Okay, so they're asking for x value, so they gave us the y value. They said, okay, well, when our function is at height 6, what are the x values? Is there more than one? Is there only one? There is only one, and the x value that goes along with that is 5, so we say x is 5. Let's go ahead and clean up the graph. We've drawn all over it, and we'll erase some stuff so we can answer, I think, 2 more questions, okay? Number 14 says, where is f of x, that's your y, where is y greater than 0 on the graph? Well, there's part of it right there that I just highlighted in this weird purple-ish color. So from -4 to -1, it looks like it's greater than 0. Greater than 0 means above the x-axis. Okay, we won't include -1 because we're not saying it can be equal to. So just strict inequality. All right, and then from -1 all the way up to 12, it is above. Now I get to actually include -4 because you got a dot there. We can't include -1 because at -1 the value of the function is 0, and 0 is not greater than 0. Okay, and then we're going to have a union at -1, and then we're going to go -1 all the way up to 12, and then for the same reason, 12's a 0, so 0 is not greater than 0. Okay. All right. Question 15 says, okay, well, where is f of x less than 0? And that's where we're below the x-axis, and so that looks like 12 to infinity and beyond. Okay. So you notice that when we were writing intervals, the only thing that we used the y-axis to actually use y values was the range. Everything else, domain, domain, increasing, decreasing, constant, and also these questions about where the function is greater than 0, less than 0, could possibly be greater than or equal to 0 or less than or equal to 0. All of that is doing x. Only the range will do y. Okay, so the next part we're going to shift gears a little bit. We're going to just throw in a little easy topic. We're going to talk about lines just a little bit. Later in chapter 4, we'll actually do a little bit more of a treatment of lines. So what we're going to look at is lines in standard form, how to graph them, and then also horizontal and vertical lines. So we snuck in a horizontal line, I think, in this problem we were just looking at. Anyways, so let's move on to the next screen, and I will accelerate the writing. Okay. So there's a little bit of a review of graphing lines using the x and y intercepts. If you want to find the x-intercept really of any function, you're going to plug y equals 0 in and solve for x. Sometimes y might be fx instead, or gx, or whatever we're calling it. To find the y-intercept, you're going to plug x equals 0 in and solve for y. Typically, that's the easier of the two if it's a function. Okay, so let's accelerate our writing a little bit. So I'm going to say this works best in when the line is in standard form. That's ax plus by equals c. And so you got the x and y on one side and then the constant on the other. Sometimes people will say, oh, well, your a, b, and c shouldn't be fractions. We're not going to get that technical in this. It's just doing the x and y intercepts. Okay, so we're going to find the x, y intercepts, and then we're going to use that to graph minus 2x plus 5y equals 10. We'll do a little t-chart, x, y, 0 for x, 0 for y. We'll plug in 0 in for x, so negative 2 times 0 plus 5y equals 10. So 5y is equal to 10. Divide both sides by 5 and you get y is equal to 2. Okay. Now the other one, we're going to plug 0 in for the y, so we'll have minus 2x plus 5 times 0 is equal to 10. So that says negative 2x is equal to 10. Then we would have to divide both sides by negative 2, and we get x is equal to negative 5. Okay. All right. So we'll draw in our x-intercept. That's at negative 5 and 0, and our y-intercept is 0 and 2, and then connect our dots. And then draw our line. And then label our line. Okay. All right, we're going to look at one more as an extra practice problem. So same thing. So we're going to find the x and y intercepts, and we're going to use them to graph. This time I think we're going to do minus x. I'm sorry, not minus x. X minus 4y is equal to 8. Plug in 0 for x, plug in 0 for y. Okay, so we got 0 minus 4y is equal to 8. We'll divide both sides by negative 4, and we'll get y is equal to negative 2. And then we have x minus, and then plug in 0 for y. 4 times 0 is equal to 8, so that's nice. X is equal to 8. So you got your y-intercept at 0 and negative 2, x-intercept at 8 and 0. So we'll go ahead and plot those points and connect our dots. All right, so that's it. I apologize if you hear the cat here. He's left me alone all day today, but as soon as I want to make a video, he's all over me. So I may have to pause if he gets a little bit too out of control here. Okay, so moving along. Horizontal lines and vertical lines. Okay, so I'll speed it up and read it for you. Okay, so vertical and horizontal lines. Vertical lines have the form x equals h. There will only be an x in the equation. I said vertical, I hope. Vertical lines have the form x equals h, only have x in the equation. Horizontal lines have the form y equals k, and there's only a y in the equation. So we're going to do two examples of graphing some vertical, one vertical and one horizontal line, just for the practice. So if we want to graph 2x minus 6 equals to 0, it's not solved, x equals, so we have to solve it, so we would add 6 and then divide by 2, and 6 over 2 would be 3. So we come over to 3 on the x-axis, draw a vertical line, label it. For number 19, we'd graph y equals minus 2, drop 2 down on the y-axis, and then draw your, draw your horizontal line. So those aren't too bad to do. We're going to look at another, what do we got, another graph, and they're going to ask us 1,000,001 questions. Well, not quite 1,000,001, but they're going to ask us a whole bunch of questions about it, and they'll ask about a local min, maximum, minimum. We'll kind of do a formal definition of mins and maxes at the end. We did a little bit with the previous graph that had a lot, well, no, it was the first one where we had a bunch of questions. Okay, so let's go ahead and take a look at it. So again, you'll have something kind of similar to this on your homework. this is the exact same graph on the nodes. It does have something called a vertical asymptote. That's that red dashed line, and you notice it is a vertical line. That's x equals -3. So when we get into chapter 5, we'll be graphing rational functions, so we'll graph things similar to this. This one's on a little bit more of the complicated side on how to graph it, but we'll do some stuff similar to that. Now, if you got a vertical asymptote, that means that value is not in the domain. So the particular value is -3. So -3 is not going to be in the domain. And the interpretation here is, I'm going to draw in all those arrows there, so it's going to continue indefinitely to -infinity, and then as we get on either side of the -3, both branches are going to go down forever. Your graph typically does not touch its asymptotes, never touches vertical asymptotes at least, and then it's going to go on forever up on the right hand side there. The only value that is not covered in the domain is the vertical asymptote of -3, so we're going to have to hop over the -3. Okay, for the range, it does appear to go everywhere from -infinity to infinity. All values of y are taken. We're going to do the same question of x-intercepts and zeros. So your zeros are the values where we cross the x-axis. So that's -1, 1, and 5. As ordered pairs or x-intercepts, that's -1, 0, 1, 0, and 5, 0. F of -4, the y value when x is -4 happens to also be -4. F of 1 happens to be 0. We already have that. That's your ordered pair over here, 1, 0. So when x is 1, the y is 0. Okay. 25. F of -1, we want to know, is that positive, negative, or 0? And we actually have that up here as a coincidence. That's one of our x-intercepts, so that's 0. Okay. 26 is asking us how many times do we cross or intersect y equals -5. So number of intersections with y equals -5. So go ahead and sketch in y equals -5, and it looks like it crosses twice. Okay. For what values, I should say what values of x, does f of x equal, so what values of x does f of x equal 5? So that is a y value, so we're going to look at where does the function get to a height of 5. That looks like at 6, when x is 6. Sometimes there might be other locations. We'll try to get that back. There you go. Sometimes there might be other locations where it might be the height of 5. So for example, if we looked at where is it height -5, that looks like 2 locations, probably maybe slightly before -2, so maybe like -1.9 or something like that, and then slightly before -4, so maybe like -3.9 as maybe a ballpark guess. Okay, so let's go ahead and clear up the graph here with all that clutter there, and so now I think the last couple of questions are about where's the function greater than 0, where's the function less than 0. So let's clear that up a little bit. Alright, so intervals for which f of x is greater than 0. Again, that is communicating in terms of x on the x-axis, no y's. Alright, so in green there I have from -1 to 1, and then also from 5 to infinity it is above the x-axis. So that means everywhere else it is going to be below the x-axis. Okay, so that'd be -infinity all the way to -3. We cannot include -3. -3 is not in the domain, so -3 is off limits for everything. Okay, and then minus 3 to minus 1, and then from 1 to 5, it is below the x-axis. Okay. All right. If we want to find a local max, we do have one. The maximum value there is 2, and that's when x is equal to 0. So that's top of a hill there, and then the bottom of a valley there. That's the minimum there. It's about -4, and that's when x is equal to 3. Okay. And so there's 1,000,001 questions there. I guess we could have done increasing and decreasing as well. So we could say we are decreasing. So where are we decreasing? Let's add that in. So decreasing. We are decreasing from -infinity all the way to -3. So we're sliding down. Let's see where else. We are decreasing from 0 all the way to 3. I shouldn't use union. 0 to 3. And then where are we increasing? So we'll use a different color. Maybe we'll do the orange. We are increasing from -3 all the way up to 0. Again, I'm using the x's, not the y's. And then we're increasing from 3 all the way up to infinity along the x-axis. Now, one way I know that I have a maximum is if I go from increasing to decreasing. Where that happens, most likely I'm going to have a max as long as the function's continuous. We're not going to get into anything too crazy. And then if we go from decreasing to increasing, then I'm going to have a minimum at that location. So that'd be another way, and we use that in calculus as a means of finding mins and maxes. Okay, so last thing we're going to look at is we're going to kind of get a more formal definition of extrema, mins, and maxes. We'll restrict ourselves to local mins and local maxes, kind of the formal definition, and then we'll do an example of that. Okay, so I'm going to speed it up a little bit. Okay, so extrema, that means minimums and maximums. So we're going to let f of x be defined on I. We're assuming I is an interval. Okay, so here's our interval I. Then we'll draw some function there. So intuitively, there's about a max, there's about a min, there's about a max, there's about a min. Okay? All right. Here is going to be our interval j, and then we're going to pick on this value here as a maximum. Okay, so there's your interval j, and we'll say that that location there is a comma f of a. The x value is a, and the y value is f of a. So we say f of a is a local maximum of f if there is a subinterval. So that subinterval is j. So that subinterval includes our hill there, such that on our little subinterval, for all a in, not for all a, excuse me, for all, oh, no, we're good. Sorry, I was not reading it correctly. All right, let's go again. F of a is a local maximum of f if there is a subinterval j such that also a needs to be in j, and f of a is greater than or equal to f of x for all x in j. So what that says is a is the tallest point in that interval j right there. Okay, so it's the king of the hill. Okay, for the minimum, it's going to be you're the bottom of the valley. Okay, so for a minimum, we'll have to change our picture up a little bit. So we'll go over to a bottom of the valley. So there it is. There's our new interval j, and we'll pick our point A and f of a. Okay, all right. So f of a is a local minimum of f if there's a subinterval j. So we'll look at kind of like a valley, such that a is in j, and f of a is going to be less than or equal to f of x for all x and j. So it's just the shortest point there. Those are local. if you're looking at global max, sometimes it's called absolute max or local global minimum or absolute minimum. They're talking about the highest or lowest on the entire function. Now, if your function goes to positive or negative infinity, then you're not going to have absolute mins and maxes. You may not even have local mins and maxes. So that's why we need to look at the picture to identify it. And so what we're doing in college algebra, usually we're going to have the graph. And so from the graph, we'll be able to interpret where the mins and the maxes are. Okay, so we're going to look at one more example, and we'll do the mins and maxes. I think we'll do some increasing and decreasing also. So this same graph is in your notes. You'll have something similar to it in the homework. So the first question we're going to look at is where are we increasing? So I've kind of highlighted it there. It doesn't quite line up on an integer, and that's all right. We'll have to ballpark it, but I found the part where we're going up, and it's maybe about negative 1.5, and then maybe about 2. Okay. So then this function is going to continue indefinitely, so it's going to be decreasing everywhere else. So it's going to be decreasing from minus infinity all the way up to negative 1.5, and then also from 2 to infinity. Okay, and so you do see that we went from decreasing to increasing. So we're going to have a minimum there, and then we went from increasing to decreasing. So we're going to have a maximum there. So 34, we're going to have a local max, and the maximum value is about 4.25. If you're doing it on the homework, it's got a little bit of tolerance, so I think you can probably get away with saying like 4.5 or 4.1 or something like that. It'll be okay. It's got a little bit of tolerance to it. So we have to do our best guesstimate because we don't know what the graph of the function is. And that occurs when the x is equal to 2. The local minimum occurs about, looks like about negative 275 is the y value, and that's when x is about negative 1.5. Again, there's going to be some built-in tolerances there, so if you're slightly off, you're not too far off, then the homework system should be able to take your answer just fine. Now, this function goes all the way up to positive infinity and negative infinity. The range is all real numbers, so it does not have a global minimum or a global maximum. There is not a tallest or shortest point on this particular graph. All right, so that about wraps up section 3.3. We'll see you next time.